Welcome to our Pheno-Talks. This time, we are having here from Strube, Christian Hügel with us, and we're discussing the challenges for the industrial utilization of advanced phenotyping sensors. As always, in the beginning, I'm doing a bit of housekeeping. So what is the aim of the webinar series at all? Within the Fraunhofer Pheno-Talks, we would like to discuss with various persons from industry and university the challenges for the industrial utilization of advanced phenotyping sensors and provide here a platform to discuss these topics in a wider area. So the whole webinar series is hosted by Fraunhofer BWSF and the IPPN in the Advanced Sensor Applications Working Group. So again, for all the persons who were here, like not the first time, you can at every time ask your questions. For this, there is on the top right of your screen a Q&A button, and there you can ask the questions. For all the questions, they will be moderated, meaning they not instantaneously appear. So we will read them and then publish them to the audience. So ask your questions, whatever you would like to, share information if you want to enlighten us with some more insights. And of course, respect also with our industrial clients that we have sometimes confidential projects and that not all questions can be answered. But however, in this environment, up to now, we've seen a very good and respectful communication. Looking back to our previous webinar series, we had tried to maintain a regular schedule for one webinar per month starting in April. And now here in June, we're having Christian Hügel here discussing about phenotyping solutions at Strube. And after that, we will discontinue the monthly schedule for a while due to the summer break, and will continue in September this year with the next talks from Jennifer Clark and Dr. Jan Behmann. So for more information, stay tuned and look at our Pheno-Talks webpage. The speaker today, as I mentioned already, is Christian Hügel from Strube. And the title of his talk is PhenoBob and BlueBob, High Throughput Phenotyping in Sugar Beetle Fields. And a bit more for the background of Christian Hügel. He studied physics in the University of Erlangen-Nuremberg. After that, he stayed at the Fraunhofer-Institut for Integrated Circuits and continued then as a head of department in Strube starting 2018, and since then is now heading the department of the quality control of sugar beet seeds. So for that, I would like to welcome Christian Hügel. Thank you very much, and looking forward to your talk.
Yeah, Stefan, thanks, and thanks for having me. As Stefan said, I was a long time also employee at the Fraunhofer-Institut, so this today feels a bit like home. So just let me share my screen. And so the topic of my talk, as Stefan said, is PhenoBob and BlueBob, high throughput phenotyping in the sugar beet fields. And so maybe the first question really to ask, how does Strube as a breeder of sugar beet seeds and other seeds come to phenotyping? Because as you can see on this slide, this is our actual product. So this, for those who don't know, this is sugar beet seeds. We also have some other crops that I won't talk about today. And so our strategy is you can optimize what you can measure. And for that, we are developing a lot with Fraunhofer together on different quality measurement methods and machines and so on. So just to have an overview, we have seed measurements, CT on seeds in the lab. We do measurements on on seedlings in the field, in the lab as well, so which we call phenotest. And to kind of get a full picture, we have phenotyping in the field with our PhenoBob, where we are looking at early plant development. And we have all these technologies developed together with Fraunhofer. So we have a long history together, not only my personal history, but also the company with the institutes. So today we focus on the field, and that's where we start. First of all, what does interest us in the field when we talk about high throughput phenotyping? For seed quality research, which is my main topic in the company, we are talking about automated and digital measurement of field emergence in the field, and that at the cotyledon stage. So really immediately after field emergence, on the first day when the plants kind of grow out of the soil. We measure dynamics of this field emergence, and after that also mortality after emergence, so plants that emerge and die off afterwards, and we can distinguish that from plants that don't even emerge. And after this whole counting of emergence on different aspects, we also monitor early leaf development in the field, and this on the basis of individual single plants, not on averages of whole microplots, for example. This is how it looks like. So we have our PhenoBob, and just so you have an idea, such a microplot consists of like 3 rows with a length of around 7 meters, and so we talk about 100 plants per object in the field, which we measure. So our PhenoBob is an autonomous field robot, which actually we use it as a tool carrier in the end. The robot itself is developed by Nanotechnologies under the name Dino, actually for weeding in lettuce, for example, and salad stuff and so on. But we purchased the robot, removed the weeding tools, and installed cameras under the robot to perpendicular to the soil to measure at a really high resolution the sugar beet plants really early after emergence. We use multispectral cameras. I guess you kind of have heard about this approach in other talks, which is kind of the go-to when you measure plants in the field, or often these kinds of cameras are used. And just to give you an idea, so we're navigating with RTK GPS, which is quite common in agriculture because you have a navigation precision of around 2 centimeters. So yeah, much higher resolution than you know from the car. The robot can drive with up to 4 kilometers an hour, but we measure at around 2.4 kilometers an hour, which has a lot to do with the optics and lighting availability in the robot. But still we can measure something like 340 plots per hour, which is the equivalent of 12 persons counting. So really, first of all, much higher capacity, but also on top of that, obviously with the data that we can acquire, much more useful information than just counting with personnel, which, by the way, is still for the most part in field research the go-to method to count with people. Of course, drones and so on are used more and more, but especially when plants are really small, drones get at their, let's say, limit of useful resolution, and so still people are used a lot as well. So just that you have an idea. On the left, you see kind of a color image that we record during our measurements. On the right, the corresponding near-infrared image, and that is it's just useful to use near-infrared for green or chlorophyll detection in the end, because green plants have a much higher reflectance in the near-infrared, so roughly from 800 nanometers to 1000, which is covered by common CCD sensors. And so you can use the near-infrared for detection and work with color more specific and after steps for later analysis, for example. So the first thing that we do in the field is we record plants, the same position in the field several times. As you can see, you have this kind of piece of wood, which is the same in all measurements. So these are really the same plants. We geolocate every individual plant after detection with its RTK coordinates, so we know the position of every plant with a precision of 2 centimeters roughly. And with that, we can, first of all, find each plant again after some days of measurement and evaluate kind of the time series of every individual plant. This is one thing that we do. And on the other hand, we have to detect, okay, which are the plants that we want to evaluate. So which are the sugar beet plants? And as you can see in this image, we have other plants that also emerge, which are wheat plants. They don't interest us. We don't want to count them or further evaluate the leaf area and so on, at least for our sugar beet research questions, let's say. Obviously, there are other questions where the wheat plants are interesting as well. So in this step, we also already have to do an automated classification of the plants. The go-to methods nowadays are obviously artificial intelligence approaches, deep neural networks, and so on. And yeah, that's what we're using here as well. And so just to give you an idea, here, for example, you can see sugar beets that were detected in the cotyledon stage. Yeah, sugar beets after several weeks of growth that we can detect as well. And so we learned things over time. So here on the left, you can see an approach that didn't work at first, but I give you some seconds so you can see, maybe you can find the sugar beet and to not make it last too long. So obviously the sugar beet is here, but what is also interesting is, well, there's another one on the top right here in the image. And so even if it's overlapped by a lot of, this grassy weeds, we still are able to find it with the current approach. And so with this image, I always tell, okay, maybe we have to do a trial to find sugar beets in the football field, really on completely grass-covered soil, so to speak. Yeah, also other difficulties that you have in the field are especially, like you can see in these two images, you have sugar beet plants at a quite early stage. So here in a two leaves, cotyledon stage still, here at the two leaf stage. So that means you have still the cotyledons here and the two first true leaves, but you have often wheat plants that emerge really near to the crops that are of interest for you, and they usually also touch, and so you get really often problems with classical image processing approaches. But yeah, with these artificial intelligence approaches, you still can only detect the relevant plants that you're interested in. Also, for the people with a background in measurement, what we also solved in our project is a difficult situation that you can see in this image. So here we have sunlight and shadow in the same image, and usually this is really a challenge for automated image processing because of the high dynamics difference in the sunlit areas and also in the shadowy places. And so what we developed is also an integrated lighting system that enables us to measure these two lighting situations in the same image without using kind of an additional screen that kind of, whoa, go away. That uses kind of a bulky shadowing screen or a screen or something, because this is kind of unwieldy and not really useful, especially in agriculture. Another thing also that surprised us a little bit, if you can see here, for example, the detection algorithm is quite strong because it also detects sugar beet plants where the leaves have been eaten. Still the plant survived, but we can find it. Also here, the cotyledons of this one have been eaten as well, but still works out pretty good in terms of detecting the correct plants and ignoring wheat plants, for example. The last challenge also is, for example, even sugar beet plants, two sugar beet plants, like you can see here, that touch and overlap, and still we are able to detect both plants individually and could evaluate them individually. Even this is more an error in seeding, to be honest, but still the algorithm can detect both plants and distinguish them from each other. So yeah, this is the plant detection. So what do we actually do with it? As I said, the first focus of interest for our PhenoBob evaluation is counting of field emergence, damages, and mortality. And so to give you an idea what we do there, Here we have again the same, another position in the field, but still the same, measured 3 times. And here we monitor the growth and the development of this example plot. I mean, it's in the end, it's six plants, but still on the first day, for example, we count the 5 plants that have emerged. After a week, okay, we count 1 less. Okay, obviously, okay, well, maybe 1 was eaten, but here you can see the first error that we get. 1 didn't emerge on the first day. It emerged on this till the second counting, but we lost 2 other plants. And so this is just an example, obviously, but still, when you count this the situation with people, you make more or less 2 errors, because on the third measurement, obviously the plants have continued to grow, but nothing more happened because all 6 positions that have been seeded have emerged. But we never really counted kind of that all plants that have been planted have emerged. So, and that is an important question for us. Because the actual field emergence is 100%. All the plants that we have put in the soil have emerged, and so seed quality has done its job more or less. Because yeah, even if they didn't emerge at the same time, all seeds generated a plant, and due to other factors, that means loss of plants or after emergence mortality, we have lost part of our emerged plants. And also what we can see on top of that are 2 other effects. First of all, you can see the growth development of these plants. So this one and this one emerged early, grew big, everything is fine. So this one is kind of small and, well, not so well developed like the other ones. And that's obvious because it emerged later. And this one is small as well, even if it emerged at the first day, or we could see it in the first counting. And this is an interesting one because here also the leaves have been eaten, which you can see on the second day, because sugar beet leaves don't really grow back. The leaves have been eaten, the plant survived, but still it has a growth depression compared to how big it could have been when it wouldn't have got any damage on that. So, and these are all really interesting and important info for us, because we can analyze it for every individual plant. And this is really a strength of the system, and especially the geolocation of every individual plant. And the other approach that we do is plant development over time. So here I can show you another time series with plants that grow, and in the bottom you can see the development of the leaf areas for these individual plants. So, and after scrolling through also with the corresponding numbers and coloring for every single plant, and the gray ones in the back are, well, the other plants of the same plot. So you can see we have kind of plants of the whole distribution that have emerged for this particular object. And yeah, here you can also see some interesting things. For example, number 2 and 4 developed early, well-developed big plants. You can see for number 2 that we are more or less at the limit of this perspective for phenotyping, because we have this perpendicular perspective from the top, and as soon as the plants, the leaves start to tilt or kind of roll up and so on, you get a bigger and bigger error in the area that you can see, just obviously by the cosine error, which is quite a big percentage of the possible area that you can see. For example, number 4, even if this one is also not completely flat. But number 2 just is more or less the same size, but loses due to the tilted leaves in visible leaf area, for example. But more interesting are actually the other ones, the ones that are back in growth. For example, number 1, this one is, well, almost done. You can see it stopped development somewhere around day 31 and didn't really grow more, and yeah, it will not survive, unfortunately. And the really interesting ones are number 3 and number 5, because number 5, this one here, also stopped development day 36, and you can see it's a little bit lighter in color, a little bit browner, and will also not make it. But number 3 still seems to continue to grow, and this is also quite an interesting case, because when we go back in time, we can see number 3 is this one. This one just has bad luck, because there's kind of a clump of soil, and plant emerges a little bit, but really can't find really through, and takes several days to push by. And so, okay, it has had to put its power in something else than really growing big, but made it. Still, you can see, okay, it's a growth depression, which is just an example for every other possible example of depression, for example, by herbicide treatment or other things that kind of stop development for some time because plants got some kind of stress. But yeah, survived it and continue to develop. So yeah, this is kind of a second example of really useful data that we can generate on individual plant basis and evaluate what is happening in our field trials for different treatments, for example, be it herbicide treatments or other treatments, be it for different varieties with different genotypes that have different capabilities for interesting traits for breeding, for example. So as I said, we are more or less at the limit of the 2D perspective, but this is an example of a research project that we also did together with Fraunhofer and the Bayerische Forschungsstiftung, which goes to 3D data, real 3D data, and the approach how to extract real 3D leaf data from point cloud measurements of individual plants, as you can see here. So in red, you can see measured point clouds, and in the video shows kind of an iterative fitting of a model leaf to these individual measurements of plant leaves. And the idea here is by doing this fit and knowing the transformation of this model leaf, you can extract parameters like curvatures of the leaves and waviness and so on, and use that to model leaves, for example, like this. When we take a measurement of a whole plant, first fit the leaf areas, and here you can see, for example, the 3D curve of the leaf axis for those 4 leaves. And not only that, I mean, after that, you don't need the measurement data anymore. And so you can extract different rolling parameters and real 3D curvature data that you can use to compare varieties, for example, or other interesting traits like, for example, leaf angle, which has an influence on resistance against a lot of sunlight, for example, when you have really what's the word? Steile Blätter. They are not so susceptible to a lot of sunlight, for example. So yeah, these things we have not implemented yet in our real-time evaluation, but still have it on the list, so to speak. This is kind of the phenotyping approach that we do. And now to come really back to one of the first slides, where we have our data of the plants in the field, and a step that we decided in 2020, as we knew, okay, we know anyways the position of our sugar beet plants, and especially we know where the wheat plants are. So we decided to take care for agriculture of this one in particular, because the other thing that we developed, and now we are at our second robot, which is called BlueBob, is an automated mechanical weeding system, first for sugar beet, later also for other crops. Which is exactly this one is the problem, because removing these wheat plants in the row in organic sugar beet, so when you are not able to use herbicide, this wheat plant and obviously all the others in the row are a problem. The ones that are outside the row you can just remove with conventional weeding, like it is done for 50 years on tractors. But working especially in complicated plants like sugar beet in the row is a real challenge, where you have to know the position of your crops. And so in 2020, we still started with the same robot, but did kind of a proof of concept, like you can see here on the right, where we used our knowledge of the position of the sugar beet plants to use active tools and remove wheat plants in the plant row. After that, in 2021, we further developed that project with also a new robot, as you can see here. And the concept is to have the cameras in front of the robot, active tools here in between the wheels, because this is quite convenient, well, tool carrier concept. So we installed six cameras and 6 weeding tools. So we have a full field weed management on that robot. The challenge in 21 was, okay, first of all, this working on 6 rows, but the challenge was to port the whole data analysis and decision where to weed and where not to weed on the system in real time, because for the phenotyping robot, we can just do that offline on the server. But still also with our knowledge and experience, especially for very early plants in the field and detecting them, we can weed really from really early, so from the first true leaf stage till row closure, because we have this experience from the phenotyping robot anyways. In 2022, so last year, we further developed the system, went to a more pre-series stage, and also we're able to work at a weeding speed of 2 to 3 kilometers an hour, which is 3 kilometers an hour is more or less the maximum for everybody who is working in the row, just because of the amount of soil that you move with opening and closing the tools or kind of interacting with the soil in the row. But still, this gives our BlueBob an acreage per season of around 30 hectares, assuming that you have to weed more or less once per week. Here, after a lot of talk, I can show you a video of the working 6 rows. I hope it's not too choppy due to maybe an internet connection. And so every row works independent from each other. And our approach is really with measuring the field exactly in the moment of weeding to weed without any pre-existing knowledge of plant positions or something, except obviously that's sugar beet plants that we that are the crops. But so this is our second kind of path that emerged from the same approach of phenotyping in the end. So why did we do that? Because I mean, now we are really far off from sugar beet breeding. The scientific question is maybe easier to understand, but still, first to do a step back. When we look at farming, there are really a lot of social challenges, and they are becoming more and more difficult, especially in organic farming. We're talking about a shortage of qualified labor. Also, when we talk about weed removal, for example, it's really difficult to get people. It's okay, and when you have people, they cost. Obviously, you have personnel costs, but you need a lot of people, and they are difficult to get. And that is really even a bigger challenge than the costs themselves. We have a lot of structural change in rural regions, and the other step is obviously public opinion is changing and shifting a lot. So the trend is going more and more to reducing herbicides, but also avoiding herbicides completely. And people want affordable organic products, and so this is one part of the equation. Agricultural challenges are there for sure. Climatic changes, also scarcity of resources, and more legal requirements, again, for the reduction of chemicals in particular, because that is, the legal requirements are obviously a mirror of the social opinion. And so sugar beet cultivation becomes more and more difficult because more and more herbicides are lost just for use. And obviously for us as a breeder, also there's a certain incentive to keep sugar beet profitable and keep sugar beet in Europe, because I mean that's for Strube as a sugar beet breeder also an important aspect. And just to give you an idea in terms of personnel costs, because outside of agriculture that's not really known, but really in organic sugar beet, for keeping 1 hectare of sugar beet weed free, and that means really just weeding in the row, because between the row that you can remove with a tractor, but in the row you pay something like 3,500 to 5,000 euros for 1 hectare, depending a bit on the pressure of weeds. With a system like the BlueBob, you can reduce it roughly 80% of these weed plants. So you can reduce these 3.5 to 5,000 hectares to roughly 700 to 1,000 euros per hectare. And with the acreage for a season of 30 hectare, that adds up to 80 to 120,000 hectares just for really weeding. So these are costs that when I heard them the first time, they really surprised me. That's on such a high level. But on the other hand, that gives us the opportunity to do these developments for obviously expensive systems in the beginning, because we have a lot of technology, we have a lot of hardware, but still, and also this is what we learned from farmers, these systems are really well received. This is kind of also helps us all who work in this field to develop these systems. So yeah, to close in the end, we are working on solutions for agriculture in the end. Also, what we are building is completely away from the robot, because actually, as you've heard, the robot for us is just a tool carrier. We need some means to drive through the field, and so what we're doing right now is also to install this weeding approach on a conventional implement for a tractor. We will continue with the BlueBob, but there will be farmers who are interested in field robotics, but there will be other farmers who will just want to use their tractor. And so this is kind of a two-way approach, and the market is big enough for both approaches anyways. And on top of that, as we are coming from the phenotyping background, there are also some things that we think about to integrate in this weeding robot as well. For example, something like a plant population mapping or plant size mapping, where we can use these phenotype ideas where we come from and bring that also as an additional benefit to the farmer. To give him some more information about his fields, for example. So what the partners who we did the development with, all these robots in the end is obviously FraunhoferIIS, with whom we did the development of the detection systems, the image processing, AI development, and up to in the end signal that opens and closes the weeding tools. Nio Technologies, who is our partner with the robotic carrier platforms. And we were kind of the industrial partner who integrated the systems and brought everything together to work in the field and offer that either for us or use that for our field research and offer that to the farmers for the weeding solution. So yeah, thanks for your attention. And if there are questions, I think we can discuss them.
Oh yeah, thank you very much, Christian, for the nice talk, and also that it still feels coming home if you have like participated in a webinar series. So that's really, I'm glad to hear. So there are a few questions in the chat. So for everyone who still has some other questions, don't hesitate to now type them also in. In between, we're gathering some new questions. Just one from my side. What was like the biggest hurdle for you to start with like this, technologically approach for weeding and phenotyping in Strube? What was the hurdle? What was the hurdle you were seeing?
Yeah. For that, we have to go back to the year 2007. So yes, no, because the predecessor before the PhenoBob as a field robot was actually a system. I should have let the slide in, but I removed it. Was a measurement system for the field, which was, well, mobile, yes, but it was kind of 4 meters long 100 kilos heavy laser scanner system that had to be carried from one plot to the other. Then it did like 2 minutes of measurements while it scanned the plants. So that was the first measurement system that Strube used since 2007. I know that because at my time at Fraunhofer, I was working on that system several times. So the history goes back a lot. And so, but the system was very innovative because with that one, Strube could already measure 3D data that we cannot do right now with the PhenoBob as well. So it was heavy, but it worked really. But yeah, that the system was in use till something like 2015 when it was blown away by a strong storm and really was destroyed. So after that, Strube had to was trying on a different project, but that didn't work out really well, and so they came back to this robotic solution, and there was not really a big challenge because Strube realized really early how valuable the data was, and so it was not really a challenge to go there. It was more a challenge to find a technology that could do that. Okay. Because also the first Dino was published in 2017 on the Agritechnica in Hanover, and in January we bought the first robot, and so that was really Strube was waiting for the technology to be ready to be used for this, and so there was no challenge in the end. I don't know if it was a challenge to get the money together in the company because I was not there yet, but yeah, and that was also, I mean, my very first slide was kind of these measurement technologies in the lab. CT on seeds, that was developed with Fraunhofer together more than 20 years ago. CT on seedlings was developed from 2015 or something till 2018 or so. So there was always Strube was always interested in developing these technologies. So there was no really challenge to go there, more really finding the correct technology to measure what was kind of the focus on in terms of the data.
Yeah, I'm glad to hear. So it's good to be in that kind of environment now for you, I think.
Oh yes, for sure.
And another question, just from my side, maybe you know about, you showed the results for the deep neural networks classifying where a sugar beet is or not. Do you know how many labeled data sets you used for that?
Yes.
Do you want to share that?
Let's say in the tens of thousands. Let's say like this.
Okay, I'm not asking more than that. Okay.
Yeah.
Just for me, it was like interesting because getting to this data is, I think, quite a lot of the challenge by itself.
Yes, for sure. I mean, that's always with artificial intelligence approaches. You have to put the sweat in to classify the data. You have to check the classification. Also, you have to check your classifiers, also the people sometimes, just to make sure, because the cleaner your data set is, the better your models are working. That's just like it is. I mean, you don't understand how they classify, and it's really, especially for people who come from conventional image processing, it can be sometimes a bit scary, the lack of understanding how the classification really works, but the results are really impressive. That's how I have to say it.
So thanks for that. Then there were another question about, what is your ground truth for the automated emergence evaluation? The manual visual assessment, is that one of the ground truths?
Yes. Okay. Yes, and I mean, we have both. We have the raw data anyways, and so we can check that against the detections in the end, and so we have both, and we can compare also both.
Okay. And then there was another question about the in-field operation. So how automated the robot really is. So is an operator at the field needed, or how is this done?
Okay, it depends. Let's say like this. So the robot, you have to bring him to the field, and you have to put him kind of in the first row, and then you press OK play and use this field map, and then the robot really navigates autonomously. Both robots actually. So either the PhenoBob as well as the BlueBob. And for both the robots that we have in the company, but these specific ones, there has to be an operator on the field because they are not yet certified to really work alone. But especially with the BlueBob, the follow-up, so the one that it's called Oreo from Nayo. This one is certified, as far as I know, from this summer on, because they improved the security system well enough with an additional geofencing around it and so on, to be able for the robot to work alone in the field without supervision, because that's, at least for selling robots, that's kind of, you need to do that, because else you lose all the benefit of not having somebody around.
And for the PhenoBob, another question, there was like, if you can automatically filter out plants that have died from your existing data set.
Yes, that is yeah, that's what we're doing. So that's really a parameter for our things, which is kind of post-emergence mortality. That's exactly the idea what I showed in this first three time measurement slides, that we really monitor for every plant, did it die? And then we see that in our data and can use that for evaluation.
Yeah, good to hear. And the last question we at the moment have is, what happens with the removed weeds? Do they stay on the field, and is this a problem?
Yes, and it depends. So the weeds stay on the field, and it depends, because the most weeds we really cut off, but a lot of weeds you just kind of pull out with soil movement and so on. And if it rains shortly after that, a percentage of them can grow back into the in the soil with the roots. So yeah, that's just kind of, you always have this part of a problem a bit. But for the most part, we just remove the weeds. And also an important factor for weeding is you have to be in the field as early as possible, because then the weed plants are as small as possible. And so when you pull them out or kind of weed them with these systems, they die off or dry out really, really quickly when they are small. And so those are also, there are other things to be early in the field, why that's important. But this is one factor for this question. So there is a possibility that some weed plants grow back again.
So in total, it's also really important to see about the timing when you do the weeding.
Yes.
And be as fast as possible.
Exactly.
There, automation helps. So this were the questions we had at the moment. From that point on, I would like to thank you again, Christian, for having you here. It was nice seeing you again. It was quite a long time we've seen each other. Yeah, as a short announcement from the beginning again, the next talks from Jennifer Clark and Jan Biemann will be more on the data side, and start then, September, mid-September. Please have a look at the homepage, and as soon as we have the date available, we will update it. Okay, so then thank you for having you here. Thank you for the attention of all of you and for all the interesting questions.